So in example 4 here, let's consider some data in this table. So we have data set A and data set B. And over to the side here, I have graphed that data. So here's data set A and data set B. Now, what you're seeing here, X1, this data is right here. X2 here. X3 here, and then Y1 here. Y2 data is graphed here, and Y3 data here. So that's to let us compare these data sets visually. So in this first data set here, you can see the middle of the X3 data is at about 4. The center of the X2 data here looks to be at about 6, and then the center of the X1 data looks to be up here close to approximately 12. So what we want to do with this data is measure the relationship between the between sample variability, that is variability among sample means, compared to the within sample variability, so variability of each sample. So the within sample variability, so for example for X2, is the spread of the X2 data. So this is within sample. And then the between sample variability, looking at the difference in, say, the means for those two samples. So this is between sample variability. And then remember, the F statistic compares between sample variability to within sample variability. So notice here in the X data sets, we don't have a lot of within sample variability, but we do have a fair amount of between sample. Here's another between sample variability from first to second sample. Now, in the Y data here, so here Y1, Y2, and Y3, so here's our Y2, and we see we've got quite a bit here of within sample variability in the B data sets compared to the A, and then quite a bit more here within sample variability, and the same down below. And then not as, actually the same between sample variability, because if you compute the means here, X1 bar and Y1 bar both have a mean of 4. X2 bar and Y2 bar both have a mean of 6. And then X3 bar and Y3 bar, the means of those data sets are both 12. So here we've got more within sample variability in the B data sets than we do in the A data sets. So the between sample variability for table A and table B is the same, approximately the same. However, the within variable samplability variability for within sample variability for data set B is more than it is for A. So, right, the Y data sets here are more spread out individually than the A data sets, the X data sets. So now, if our between sample variability is large relative to within sample, then that's evidence that suggests that the samples come from populations here with different means. However, if your between sample variability is small relative to within sample variability, then they probably come from populations with the same means. And then our F statistic is the ratio of between sample variability to within sample variability. So we're comparing those two types of variation and then forming a ratio. So how do we actually find these quantities between sample and within sample? We looked at visually how we would find those. So we define the sum of squares for treatments as our measure of variation between the means. So the sum of squares of treatments is defined to be the sum from 1 to k, I equal 1 to k, of n sub I, so the number in the sample, times xi bar, so that's the mean of that particular treatment, minus x bar, the mean of all the data. And we square it because we don't want any cancellation coming out. So that's deviation of the sample value and the overall mean weighted by the sample size, because we're multiplying by the sample size. And then we define the mean square for treatments, MST is how we'll abbreviate that, to be the sum of squares for treatments, SST, divided by k minus 1. And that is our measure of between sample variability. So this is dividing by k minus 1. K is the number of populations. So this is kind of finding an average of the variation between. And then the sum of squares for error is a measure of sampling variability within the treatments. And so we define that SSE is N1 minus 1, so first sample size, times the first variance, N2 minus 1, second sample size minus 1, times the second variance, all the way down to N sub k minus 1 times the variance of the last sample. So this is a weighted average here of variation inside the samples, and it's weighted by the size of the sample. So we've got sum of sample variances here, weighted by the degrees of freedom or weighted by the size of sample. So this is a weighted average of the variance of the samples. And then we define the mean square error, which you'll sometimes see denoted as SP squared, more often MSE, to be SSE, this quantity, divided by n minus k. And that's going to be our within sample variability. And then the F statistic, which is the measure of between sample over within sample, you divide MST by MSE. And then that is a statistic that follows the F distribution. And then we'll reject our null hypothesis if this F statistic, mean square of treatments over mean square of errors, is greater than our critical F value. And why is that? Well, if H0 is true, if all the population means are the same, then mean square of treatment and mean square of errors are going to be unbiased estimates of sigma squared. Whereas if H0 is not true, then mean square of treatments is going to be greater than mean square of errors, causing F to be greater than 1. And the bigger it is, the more between sample variability is greater than within sample variability. So if H0 is true, then these are unbiased estimates of the same quantity sigma squared, and they should be very close to each other.